Welcome to my channel. In this video, I am going to discuss eigenvalues and eigenvectors of a vector. Basically, it will be a series of lectures to discuss these topics. In this video, particularly, we will focus on the concept of eigenvalues and vectors, and we'll discuss permutation matrix and its eigenvalues and eigenvectors. So let us start. Eigenvalues and eigenvectors are defined only for square matrices. So this is important that it should be only for the square matrices. For rectangular matrices, it is not defined at all. So here I have shown one n cross n matrix. Here we are having n rows. These are the rows, n rows, and we are having n columns. And each row, you see in the first row, A11, A12 up to A1n. So there are n such elements. Similarly, in second row, n elements, and last row also n elements. In the same way, you will be having in each column, there are n elements. So we'll call it n cross n matrix. It's a square matrix because number of rows and number of columns are same. If number of rows and number of columns are different, then it is not a square matrix. Okay, so eigenvalues and eigenvectors are valid only for square matrix. So I have shown few examples of square matrix. See, the first one is 2 cross 2 square matrix, 2 rows, 2 columns. Similarly, this is 3 cross 3, this is 4 cross 4. Now, I'll define or I'll consider matrix as a linear operator or transformer. So what is the meaning of linear operator or linear transformation? Okay, so let us consider one 2 by 2 matrix with the element A, B, C, D, and I'll consider one vector 2 cross 1 vector, means 2 rows and 1 column, only 1 column, thus it is a vector. So remember, if matrix is generally 2-dimensional, okay, but if it is having only 1-dimensional, means either it is having rows or it is only columns, then it is called a vector, and it is called column vector if it is having only 1 column. So this is 1 column, so it can have more than 2 rows, that is possible. Okay, so it is 2 cross 1 column vector. Elements are x1 and y1. Now when this matrix will operate on this column vector, it can produce another vector of same dimension 2 cross 1. Okay, and I'll consider this thing x2 y2. This is 2 cross 1 column vector. This is obtained by taking a linear operation on this column vector using this matrix A, B, C, D. Okay, so this we write in this form. So x2 y2, this vector is obtained by taking matrix multiplication of these two. One is matrix, this one A, B, C, D, 2 cross 2 matrix, and this is one vector, 2 cross 1 vector. Okay, and this matrix multiplication we can write as this x2 is obtained as this A times x1. So you should take a product of this and this first, and again this and this, these two product, A into x1 and B into y1, then addition. Similarly, y2 would be C into x1 and D into y1 and addition. Okay, and you see x2 and y2, they are obtained by taking linear combination of these two values x1 and y1. So x1 is multiplied by one constant A. Similarly, y1 is multiplied by B, then a combination. So it's called linear combination because only the x1 and y1, its weightage are there, and then we have taken summation, right? Similarly, y2 is also linear combination of x1 and y1. Okay, thus it is called linear operation or linear transformation. Okay, here I'll consider this vector as v1. I'll put small letter v1 and underscore to indicate it's a vector, and I'll use capital letter and underscore to indicate it is a matrix. So this is another vector v2 underscore, right? So in books you will find that this matrices are denoted as bold letter, capital bold letter, and vectors are denoted as bold letter of a small letters. Okay, right. Now this one we can write as, then this v2 is obtained as product of a and v1. Okay, so a followed by v1, that is important. You cannot write v1 times a. Okay, so matrix operation is not commutative, right? So a times v1, then only it is v2. Okay, now we'll try to represent it, these two vectors, in xy plane. So this is our x axis, this is y axis, and suppose this is your v1. So this length is x1 and this one is y1. That's simple. It's okay. So we have considered one vector v1, and when this matrix will operate on this vector, it will produce another vector v2 that we can represent in this way. So this is your y2, this is your x2, so you will find this is v2. Okay, so these are two different vectors, maybe. Okay, and these two vectors may not be in the first quadrant, it could be anywhere, but for simplicity I have shown it in first quadrant, right? Okay, it depends on these values x1 and y1. If x1 y1 both are positive, then only it will be in first quadrant, and if suppose x1 is positive, y1 is negative, then it will be fourth quadrant. Similarly, you can have second and third quadrant. Okay, now I'll take one example, particular example. So a matrix is chosen as 0 1 1 0. You can notice this diagonal, these are called diagonal elements. It is 0 0. The off diagonals are again same 1 1. So for this one, you see, if this vector is having x1 y1 element, then x2 y2 will be of this form, 0 times x1, 1 times y1. So if you take combination, what you'll get? It's simply y1. Okay, similarly y2 is 1 times x1, 0 times y1 is simply x1. So x2 is y1 and y2 is x1. Okay, so do you get any similarity? So this output vector, this vector v2 is having element just opposite one in reorder. Okay, this y1 is coming here and x1 is coming here. Okay, okay, you can take one more example. Suppose if it is 1, it is 2. Okay, this is my v1, 1 2. Then you see this is 1, this is 2, this is 1, this is 2. So this is your v1 vector, this is 1 and this is 2, right? So what is your v2 vector? You see this is 2 and 1. So that we can represent here. This is 2, this is 1. So earlier v1 is, this is first 1, then 2. And for v2 it is first 2, along x-axis it is 2, along y-axis it is 1. So this is the positional vector. So you see this v1 and v2 are positional vectors, and these two are different. But you can notice here, when v1 is 1 2, v2 is 2 1. Okay, so magnitudes are similar. Okay, elements are similar. This is 1 2, but positions are different. Similarly, if I consider 0.5 and 3 for v1, so this side 0.5, this side is 3. So you see this vector is much closer to this y-axis. Okay, right now. Okay. So along x-axis only the 0.5, along y-axis this height is large, it is 3. Okay, and for this one you see this v2 will become, so this 3 is coming here, this 0.5 is coming here. Okay, we can show here as this is 3 and this is 1. So you see from earlier it was 1 2, so you see the vector v1 is moving away from this one towards the y-axis. Simultaneously the v2 is also moving away from this vector to closer to this x-axis. Okay, and here this matrix A 0 1 1 0 is called permutation matrix, because whenever this matrix will operate on the vector, you will find another vector where the elements are in the permutation only. Okay, the positions are different, that's all. So the values will remain same. So you see the first element 0.5 is coming at this end, and this 3 is coming here. Okay, thus it is called permutation. Actually permutation matrix is obtained by taking permutation of rows or columns of identity matrix. Okay, and identity matrix, you know that this is 1, this is 0, this is 0, this is 1. Okay, so if you consider if you interchange these two rows, you will find a permutation matrix. Right, now if I consider it is 1 1.5, then obviously it will become 1.5 and 1. So now you see it is coming to this side, because earlier it was 1 2, now it is becoming this 1 and 0.5. Okay, and this is 1.5 and 1 this side. So you see the changes. So can you expect that we'll find one vector v1 such that the v2 will be in the same direction. Okay, so if we come to this side again further and v2 will come also this side, we may find one vector here where both v1 and v2 will be in same direction along the same line. Okay, that we are interested here. So you see, if I consider 1 1, then obviously you will get again 1 1, because this one will come here, this one will come here, because both are same magnitudes. So again this output vector v2 will have the same result. Okay, so v1 and v2 they will coincide for this case. Okay, so here this 1 1 is actually called eigenvector of this permutation matrix. Okay, this is one feature of this matrix, because whenever this matrix will operate on this vector, the resulting vector will be along the same direction. In this case, it is not only same direction, it is also giving we are getting the same vector, but sometimes we will get different magnitude but along the same line. Okay, so eigenvectors are defined as in this way, that A into V, if V is one eigenvector, then if I multiply A into V, I'll get same V vector, but we may have one scaling factor, and that I'll call it lambda. So in that case, B is called eigenvector and lambda is eigenvalue, corresponding eigenvalue. Okay, so we are interested to find that direction V, where whenever this matrix A will operate on that vector, we will get the same direction V with some other magnitudes, may have. Okay, but in this particular example, permutation matrix, the lambda is particularly 1. Okay, right. So you see, this is the direction. So not only 1 1, if I consider 2 2, it is 2, it is also 2, then also we will get 2 2. If it is 3 3, it will be 3 3. If it is minus 1, this side also minus 1, again it will remain, b2 will be minus 1. Okay, so what is the meaning? Meaning is that 1 1, 2 2, minus 1 all are the eigenvectors. So, but eigenvalue is 1. For that matrix, eigenvalue is 1, but we'll find infinite number of eigenvectors along that line. So along this line, we'll find infinite such eigenvectors. Right? Okay. Now if I consider -1 and 1. So this one will come here, this -1 will come here. Okay. So I have considered these things -1, 1. So that I'll show here. So this is my current V1, -1 and 1. And you see the V2 will be 1 and -1. 1 is this side and -1 is this side, right? So you see this one. So this is your 1 and -1, it is your V2. So you see this V2, we can rewrite as -1 times -1, 1 is basically V1. Means V2 is just opposite of V1, negative sign of these things. 180 phase reversal, right? So in this case, this -1, 1 could be considered as eigenvector because we'll obtain the same. V2 is similar to V1, but with one scaling factor -1. Okay, so eigenvalue is -1 and eigenvector is -1, 1. This element, this vector. So basically, we will find this is the eigenvector direction. It could be 2, -2, or -2, 2, or it could be 4, -4, like that. Anything. Okay, along this line, all are eigenvectors, and for those eigenvectors, eigenvalue is simply -1. So for this permutation matrix 0, 1, 1, 0, we have got eigenvalue 1, and that time corresponding eigenvector is 1, 1, this one. And when eigenvalue is -1, I'll find another eigenvector direction, that is 1, -1, this one. Okay. Now if I consider A equals to 0, 2, 2, 0. So you see it is similar to permutation matrix, just only one change. Instead of 1, both are replaced by 2, 2. So basically the earlier matrix is multiplied by 2. Each element of earlier matrix are multiplied by 2. Okay. So for this, if I consider again 1, 1, a vector, if I multiply with this matrix, then you will see it will become 2, because 0 into 1 is 0 and 1 into 2 is 2, so it will become 2. Similarly, it will be 2 also. So this 2, 2 I can write 2 times of 1, 1. So again, you will see this 1, 1 is an eigenvector of the same matrix A, this matrix A, but this time eigenvalue is 2. Okay. Similarly, if I consider 1, -1, this direction, again you will find that it is 2 minus 2 means 2 times of 1 minus 1. Eigenvalue is 2 again. Okay. So for this matrix, we'll find same eigenvectors 1, 1 and 1 minus 1, but the corresponding eigenvalues are different. This time it is lambda equal to 2, it is lambda equal to -2. So is there any relation, straightforward relation, that what could be your eigenvectors? That will be discussed later. Now I'll consider this one. It is very well known. So this 1, 0, 0, 1. For this matrix, if I consider multiply x and y, you see you will get same x and y. So if I multiply with any vector xy, I'll get the same vector. Okay, so there is no change. That's how this matrix is called identity matrix. And its eigenvalue I can consider as 1, and its eigenvectors, all are eigenvectors in 2D plane. Okay, 2 cross 1 vector, all 2 cross 1 vectors are eigenvectors, remember. Okay. Now if I consider 3, 3 and 0, 0, so these we can write as, so if I see it is if I multiply xy, I'll get 3x 3y. That we can write as 3 times x and y. So eigenvalue is 3, and we'll find same vector xy. So I can say that this A matrix is basically 3 times of identity matrix. And when I is having eigenvalue 1 and 3i should have eigenvalue 3, so this is in general it is true. So if A is one matrix and its one eigenvalue is lambda, then small m times capital A, so this is scalar multiplied with this matrix, then corresponding eigenvalue will become m into lambda. That is true for all, not only for identity matrix or permutation matrix. Okay. So thus you see for this permutation matrix 0, 1, 1, 0, earlier the eigenvalue was 1 minus 1, it is 0, 2, 2, 0. So basically this is this permutation matrix is multiplied by 2, here m equal to 2, thus eigenvalues are 2 and minus 2. Okay, so this is multiplied by 2 and this is also multiplied by 2, so I will find 2 and minus 2. Okay, now I'll consider one more example. 3, 2, 2, 3. So can you find eigenvalues and eigenvector quickly without computing anything? Okay, that is our task. Now, can we rearrange this matrix as, so you see this 3, 3 I will put here and I put 0, 0 here. And then 2, 2 I'll keep it here and I'll put 0, 0 here. So if I take these two addition, obviously 0 plus 3 will be 3, 2 plus 0 it will be 2. Similarly, this is 2 plus 0 is 2 and 0 plus 3 is 3. So we can break this matrix in two parts. One is this one, the other one is this one. So you see this is some scalar multiplied of identity matrix and this is one scalar multiplication of permutation matrix. So we can rewrite in this way. So this is 3 times identity matrix and it's 2 times of this permutation matrix 0, 1, 1, 0. Right. So this permutation matrix we know the eigenvalue, when eigenvalue is 1, that time eigenvector is 1, 1. And when eigenvalue is minus 1, eigenvector is 1, minus 1. That is known to us. Now, I'll consider this matrix. So 3, 2, 2, 3. Now, if I consider 1, 1 vector again, so what you will get? This is 1, 1. If I multiply this two, so 3 into 1, 2 into 1, 2. So 3 plus 2 is 5. Similarly, 2 into 1, 2. 3 into 1 is 3. 2 plus 3 is again 5. So it is 5, 5. So I can consider as 5 outside and this 1, 1. So you see, whenever we will multiply 1, 1, again I will get 1, 1, but this time scaling factor is 5. So this is my eigenvector. This is the eigenvector and this is the corresponding eigenvalue. Okay, so eigenvector, this one, again we will find the same eigenvector. Okay, again, if I consider 1 minus 1, so 3 minus 2 is 1. Next time 2 minus 3 is minus 1. So this one we can write as again 1 minus 1. So it is simply scaling factor 1. Okay. So we'll find same eigenvector or permutation matrix but different eigenvalues. So what are the eigenvalues? Can we find it quickly? So if this matrix, this type of kind of matrix is the eigenvalue, we can simply find 3 plus 2 is 5. That is for 1, 1. And 3 minus 2 is another eigenvector that is for 1, minus 1. Okay, now why it is so? Okay, but this is the concept only. So you need to consider 3 plus 2 is 5 and 3 minus 2 is 1. Okay, so now we'll explore more about these things. Now if I consider one matrix A of this form, it's m times of identity matrix plus n times of another matrix B. Not necessarily it is a permutation matrix. Okay, so B could be anything, but I is identity matrix. That is important. This I is identity matrix and I'll find another matrix B, any kind of matrix. Okay, now if I say that for this B matrix eigenvalue is lambda and corresponding eigenvector is small b. Okay, and if it is so, then for this A matrix eigenvector will remain same eigenvector V, but corresponding eigenvalue will be the same plus n times its eigenvalue lambda. So m plus n into lambda. Okay. So this is my claim. Now we can prove it. So its proof is very simple. Now multiply this A with this small v again, where the small v is one eigenvector of capital V matrix. Okay. So A V. So A is replaced by A identity matrix plus A and B times V. Now we can expand it. So it will be A identity matrix V and this A, B and V, and I times V, it will remain V only. Okay, because we've shown that IV, so V for identity matrix, any vector is eigenvector, so again it will remain same vector V. But for this thing NV, if V is the eigenvector of V matrix, then we can replace this thing BV as lambda times V. Okay. So now we can take common these V vectors. So it is M, this is n lambda, M plus n lambda times V. So if I multiply small v vector with A, then you will get same vector V with scalar multiplication M plus n lambda. Thus, this is nothing but eigenvalue. Okay, M plus n lambda. Okay, so this is true. This is proved. Now if I consider 8 minus 5 minus 5, 8 of this form. Okay, so you can understand that in this case M is 8 and n is minus 5. Right? So what would be the eigenvalues and eigenvectors? So as it is a combination of identity matrix and one permutation matrix, obviously eigenvector will remain same, 1 1 and 1 minus 1. And eigenvalues we can find it quickly. Eigenvalues will be m plus n lambda. M is 8, n is minus 5, and for this one lambda is 1. Remember 1 1 lambda is 1. So if I put lambda is 1, so 8 minus 5 into 1 means 8 minus 5 will be your 3 here. And for this one, lambda is minus 1. So 8 plus minus 5 times minus 1. Okay, that means 8 plus 5 will be 13. So you see, first one will be eigenvalue 3 and second one should have eigenvalue 13. So this is the corresponding eigenvalue and eigenvector. Okay, I think you have got this concept. So what is the conclusion? If V is an eigenvector of A matrix, then if I multiply V vector with A, I'll find same direction V with scalar multiple lambda. And A must be a square matrix. And for permutation matrix 0 1 1 0, we'll have two eigenvector direction. One is 1 1 at 45 degree, and this is 1 minus 1 135 degree. Okay, that directions. For this 1 1, eigenvalue is 1. For 1 minus 1, eigenvalue is minus 1. Okay, I'll show you later that the addition of these two is sum of these two eigenvectors. So 0 plus 0 is 0. It is 1 minus 1 is also 0. So that will be discussed in one video. Then we have seen that if A is a eigenvalue, one eigenvalue of value is lambda, then m times capital A, its corresponding eigenvalue will be m times that lambda. So you should multiply with the same factor small m. So now if A is one matrix with eigenvalue lambda and eigenvector small v, then m times identity plus n times A will have same eigenvector v and with eigenvalues, corresponding eigenvalues m plus n into lambda. That is important. This m, this n into lambda, that you need to combine. We'll get new eigenvalue. So it's very quick. I hope you can quickly find the eigenvalues of permutation matrix. So this is for 2 by 2 matrix. If it is 3 by 3, 4 by 4, that will be discussed in one lectures. Okay, not in this lecture. So in the upcoming videos, I'll be discussing more particular types of matrices like rotation matrix, projection matrix, or permutation matrix with higher order. Okay. And in particular, we'll try to understand these few things. So here we have found that two different eigenvector directions, but will we get always such two different eigenvector directions for all the 2 cross 2 matrix? Okay, that we'll try to understand. And will we get always real eigenvalues? That is important. So here we have got 1 and -1 for permutation matrix, but will we get always real eigenvalues? Okay. If we don't get real eigenvalues, if we find some complex eigenvalues and eigenvectors, so then what's the meaning of complex eigenvalues and eigenvectors? Okay, so what is the physical interpretation of those things? Those will be discussed in detail, and also we'll try to find how to compute the eigenvalues and eigenvectors in a simple manner quickly. Okay, so we'll be discussing all those things in sequence. So please keep watching. So if you have not subscribed my channel, you may subscribe it. And if you like this video, please press the like button and share with your friends. Thank you very much.